Hi everyone, my name is Victor Lai with BCM and welcome to part 1 of explaining MPT. The series was created to provide an overview of modern portfolio theory, also known as MPT. Now, if you don't have much experience with investing, I suggest checking out the Investing 101 series first in order to make the most of this presentation. Otherwise, we are going to go ahead and get started. MPT was developed in the 1950s by Dr. Harry Markowitz, who is an economist, an American economist from New York, and a professor of finance at UC San Diego. Over the following decades, it was further developed by industry colleagues like Dr. William Sharp at Stanford and the late Dr. Merton Miller at the University of Chicago. Like most great thinkers, these people were ahead of their times. It took many years for MPT to be fully appreciated, but eventually it was, and in fact these gentlemen won the Nobel Prize in Financial Economics for their accomplishments. So what is MPT exactly? MPT is basically a framework for evaluating risk and return. And while that sounds simple, we have to understand that prior to MPT, there was no standardized way to do this. So imagine a bunch of people trying to evaluate an investment's risk and return. But everyone is doing it in different ways. It would be pretty confusing. It would be like everyone was speaking different languages. The genius of MPT was that it created a common language. And today, MPT has become the foundation for most of professional portfolio management. Now, as we go through the rest of this presentation, it's important to keep in mind that MPT is a theory, after all, and as such, it relies on assumptions that don't always hold true in the real world. The point is that MPT is not a tool for making precise or accurate predictions. It is meant to help establish a reasonable range of expectations, which can then be used to help make better informed investment decisions. As far as how it's done, MPT uses a lot of math, statistics in particular. For example, one of the central ideas in MPT is the statistical concept of a normal distribution. The idea is that as a sample of data gets large enough, as it increases in size, the values within the sample will increasingly concentrate around a central value. This is also known as central tendency. And if we were to plot the results onto a graph with the number of observations on the vertical axis and the value that we are measuring on the horizontal axis, we'd end up with something that looks like this, which is commonly called a bell curve. Now, to make sense of this, let's just do a really quick example. Let's pretend that we went and measured the height of every man in the United States. There would be something like 100 million measurements, which is a very large sample size. Now, if we went and graphed the results, we would find that some men are very tall, represented by the right end of the graph. Some men are very short, represented by the left end of the graph. But most men would be somewhere in between, represented by the center. And the highest point on the graph, which is in the middle, represents the most common height, which is shown here as x. For a normal distribution, this most common value is also the average value. So if someone asked us, how tall is Uncle Bobby? We probably wouldn't know. But forced to guess without any additional information, our best guess would be x, the average or most common height. Now, most common or not, with so many possible values, we're probably going to be wrong. The neat thing about a normal distribution is that it can estimate how wrong we might be. And that estimate is based on standard deviation. Now I know there's a lot of things going on this page, so let's just break it down piece by piece. First, look at the line going down the center of the distribution. It's labeled the mean. The mean is just another word for the average. Now look at how the distribution is split up into sections around the mean. Each section represents one standard deviation. For example, the section from -1 to +1 represents one standard deviation around the mean. Likewise, -2 to +2 would be two standard deviations around the mean, and so forth. The important takeaway here is that for any normal distribution, one standard deviation around the mean will include roughly 68% of all the values in the sample. Two standard deviations will include roughly 95%, and so on. And as we increase the number of standard deviations that we go out, we get closer and closer to including 100% of all the values. But we never quite reach 100%, which means that these tails theoretically would go out into infinity, with the sections becoming increasingly small, infinitely small. Now all this stuff can be calculated and proven mathematically, but how we do all of that is not really important for us right now. What is important is how we can use the findings. And that's what we're going to look at next. And to do that, let's just go ahead and continue our example. Let's say that we went and measured the height of those 100 million men, meaning we'd have a sample size of 100 million. Now, based on the data, we can calculate the mean, and let's say it was 6 feet. We can also calculate the standard deviation of the height, and let's say we calculate that to be half a foot. Well, based on what we know about a normal distribution, we can say the following things. Number one, the most common height among the men is 6 feet. Number two, 68% of the men will be between 5.5 feet and 6.5 feet tall. That's based on one standard deviation around the mean. Another way to think about this is to think that we can be 68% confident that a randomly selected man from our sample will be between 5.5 and 6.5 feet tall. Likewise, we can also be 95% confident that he will be between 5 and 7 feet tall. That would be based on two standard deviations. And we could continue to increase our confidence level by increasing the number of standard deviations we go out. Now, something to notice is that the higher the value of standard deviation, the wider the range of potential outcomes. For example, a mean of 6 and a standard deviation of 3 will have a much wider range of outcomes than a mean of 6 and a standard deviation of 1/2, which we have here. In other words, standard deviation measures the magnitude of uncertainty or the volatility of potential outcomes. And since we know that risk and volatility are the same things in finance, that means we can use standard deviation as a measure of risk. The point is, higher standard deviation means higher risk. So now the question is, how does all of this stuff apply to investing? And that's something that we're going to go over in part 2 of explaining MPT, which should be up soon if it isn't already. As for now, I hope that you all enjoyed this presentation, and if you did, then please visit BCM's website at bellwethercm.com. Click on the contact page and then check out the other social media links. Please like, follow, subscribe, and share the content. And if you or anyone you know has questions about or needs help with investing, then please feel free to contact me. Otherwise, thanks for watching, and please stay tuned for some important disclosures.